Welcome to Empowered Learning. This is the first video in the video series where we are going to discuss the concept of Taylor and Maclaurin polynomials. So in general, what we are doing here is we're taking the topic of power series and we're putting some special names on them depending upon certain conditions that we have. And so we're going to unpack all the things that we need to consider in actually knowing about and using in applications as far as Taylor and Maclaurin polynomials are concerned by asking 6 questions and answering those questions by presenting definitions, theorems, and doing examples. So in this first video, out of these 6 questions that we're going to ask, we are going to ask and actually address with answers the first 2 of those questions. And then in the remaining videos, I will go over examples, definitions, etc. to take care of those other 4 questions. Now, if you see what the notes here say, it says, remember back when we were studying several integration techniques, such as integration by parts, trigonometric substitution, partial fraction expansion, etc. And so I'm not going to read all of that to you, but the main thing that I'm trying to get at was that there were some integrals that we dealt with, or there were some functions that we were trying to take the antiderivative of. Even in learning these extra integration techniques, we couldn't do it. It was still difficult to do it. And unless we were trying to find, let's say, the answer to a definite integral where we actually had a numerical answer that we were trying to get to, unless we had a situation like that where we could use something like, Riemann sums or, Simpson's rule or trapezoid rule to be able to estimate the area under the curve, we were pretty much at a loss, for finding a way to find the actual antiderivative of a function that in essence did not have what we call an elementary function antiderivative. And all that we mean by elementary function antiderivative is just an antiderivative that's made of functions that we're used to dealing with. Okay, so like all of your logarithms, exponentials, polynomial type functions, radical functions, root functions, those kind of things that you're used to seeing. So if we could not, in a very clean and concise way, express the antiderivative of a particular function as an elementary function, and we knew that because none of the integration techniques that we would try to do would work, then again, we were at a loss. So some of those integrals will be some like what you see here, okay? And so the whole purpose of everything that you've probably learned about power series, because if you're watching this video, then you should have some knowledge about power series already. If you don't, you definitely want to go back and watch the videos that I have on that, because that will prepare you to be able to absorb what we're going to talk about here. But essentially, how we get around not being able to take the antiderivative of functions like the ones that you see here is we essentially express the function that is in our integrand as some infinite term polynomial, okay? And so that is where the whole concept of power series comes into play, in a way where we can actually use it for something tangible. Okay, so when we start putting special names to power series under certain conditions, this is when we get power series by the name of Taylor series or Maclaurin series. And I'll also make a separate video series, or a separate video, I should say, on the binomial series, which is another type of power series type polynomial that we could use to be able to express functions that we have a tough time finding antiderivatives for in that way. Okay, so the whole point of what I'm talking about here is that When we talk about Taylor and Maclaurin polynomials, we're doing it because we're using special kinds of power series to be able to express the functions of like the ones we have here in these integrands in a way to where we can get a good idea of what the antiderivative would be, essentially by using polynomials. And we know that because one of the byproducts of the fundamental theorem of algebra is essentially saying that, hey, any function that we have that can be made up of elementary functions could be expressed as a polynomial function over a given set of x values. And that's essentially all that we're trying to do here. Now, of course, the devil is in the details on how we actually do that, but that's essentially what it is that we're trying to do. Okay, so now that we kind of understand what the whole purpose of Taylor and Maclaurin polynomials are in general, what we're going to do is go ahead and run through these 6 questions. And of course, the first 2 are the ones that we are going to address in this video. And then for the remaining videos, I will address the other 4 questions. So question number 1, if we assume that any function could be expressed as a power series, what would this expression of that function look like? Okay. Number 2, are there any popular or special case power series expressions we need to know? And that's where the Taylor and Maclaurin polynomials come into play. Number 3, how can we determine if our power series representation of the function f of x that we're trying to re-represent as a polynomial, is it going to actually equal our function? So that's the third question. And we have ways of being able to tell that. For question number 4, is there a list of well-known power series representations that we can use as a reference? And so once we, of course, get through addressing questions 1 through 3, we'll go ahead and list those because you'll know how we actually came up with them. Of course, we won't do them all, but once you kind of get an idea of how we come up with 1 or 2, then you'll know, hey, this is how we do it with the rest of them. Okay. And if you're already familiar with power series, you'll kind of already know the answer to this question, but we just, cover it again here for formality reasons. For question number 5, if our power series representation of the function f of x actually equals this function, how can this information be used to integrate integrals that have non-elementary functions as antiderivatives? And of course, I kind of alluded to that already, but we'll actually see examples of that in the later videos. And of course, final question, can we multiply or divide well-known power series representations of functions in order to form other functions? And of course, the answer to that question is yes. And we're going to see examples of how that's done to be able to find out the antiderivative of functions that are like that. Okay. And some of those I've already shown you in that list of most general antiderivatives, or those list of integrals that you saw at the beginning of the video. Okay. All right. So let's dive in and go ahead and try to address the answer to this first question. So our question number 1 again was, if we were assuming that a function could be expressed as some power series, what would that look like? Okay. So to answer that question, we suppose that there is some function f of x that can be expressed as a power series. Then we know, because of what a power series is and what it looks like, then that means that function could essentially be expressed as an infinite term polynomial where each term is going to have something that looks like that in it. A is going to be a constant that we say the power series is centered about. C sub n is going to be coefficients, and depending upon what formula you use for C sub n will depend upon what they look like. And of course, n here is the counter, counting the number of terms, which also is letting us know what is going to be the power on the x minus a here. Okay. Now, we know that power series of this type will converge if we know that the absolute value of x minus a is less than r. So putting that another way, where r here is what we call the radius of convergence. And of course, again, if you're unfamiliar with power series and you may not know what that is, you may want to check that out. So here, just to kind of draw what's going on here, let's say we have some x values for which this power series will converge. And all that means is that if we add up the infinite number of terms, let's say we stick in a value for x for it, the result is going to end up being some series that actually adds up to be approaching some number. Okay. And so here when we say x minus a is going to be, absolute value of x minus a is going to be less than r, then essentially all we're saying here is that whatever x minus a is going to have to be in between r and negative r. Okay. And of course, if we're adding a to both sides here, then that would look like this. And this would go away. And essentially what we're saying here is that x is going to be some value. It's going to be centered about some value a. And we're going to go r units in a direction this way. And we're going to go r units in a direction this way. And any x value that's within this open interval here, if I plug it into the power series here, and I was to list out all infinite number of terms, add them up, it would converge or add up to some number. Okay, so that's essentially all that means. And of course, if we expand out the power series, we see that this is what it would look like. Okay, and again, we understand what this whole thing here of absolute value of x minus a is less than r means now. So as long as we pick x values in between a minus r and a plus r, we are guaranteed to have a corresponding series that will converge or add up to some number. Okay. And again, here I just list, what's going on with the, first and second derivatives or whatnot here. So if we do that, now I'll go ahead and scroll down some more and then we'll figure out what they are. So if we look at our function here, our original function that looks like this, and then we take the first derivative of it, second derivative, so on and so forth, we see that things start to change. The main thing that I want you to see here is that if I was to let x equal a here and plug that in for x here, then every term except for this one would go to 0. And then for the first derivative, if I plugged in a here, every term except for this one would go to 0. And if I plugged in a here, every term except for the first one would go to 0. Okay. And so if we keep on doing that here, we see that for f of a, f prime of a, f double prime of a, we start to see a pattern happen. Okay. And it turns out that that pattern will end up being that we have some c sub n, and we'll see this later, but I'm just going to go ahead and say it now. We're going to have some c sub n that's going to end up looking like this. Okay, where the f with the parenthesis n is just going to be the nth derivative of our function evaluated at a divided by n factorial. We'll see that if we follow the pattern, that's what the coefficients, whenever we do a regular power series, end up looking like. All right, so here the power series representation theorem is essentially saying what I just got through saying, but we're going to formally go over it now. So if a function f can be expressed as a power series centered about x equals a, then of course that power series will converge to these values here. and our coefficient C sub n can be computed by this formula, okay? And so, again, if you're familiar with power series, you've probably already seen this, but this is just formalizing it so that we can use this and move forward. Therefore, if we wanted to express a function f of x as a power series, we would just need to know how to obtain the coefficients of the power series to be able to do it, okay? So once we kind of know what's going on with the power series, the main thing is just knowing what all the derivatives of our function are going to be, evaluating them at a, and then divided by, n factorial for several values of n, depending upon how many terms we want to use to approximate what that particular function that we're trying to model as a power series is going to be. So question number 2 asked us, are there any special types of a power series that we need to know about that we can use, or as I like to say here, put into your toolbox? And yes, we have some, okay? The 3 that I will talk about in the videos that I'll create for the series will be the Taylor series, Mclaren series, and the Binomial series. And the Binomial series, it's a little different than the Taylor and Maclaurin. So again, I'm going to make a separate video to talk about that particular series, because there's a lot of other moving parts that go along with that one. So it'll probably be best if we address that particular series separately. So now let's see, what does the Taylor and Maclaurin series actually look like? So the great thing about the Taylor series is that if we're already familiar with what a power series is, then we automatically already know what a Taylor series is, because Taylor series is essentially just a formal name that we put to what we call a general power series, okay? So, and you're wondering, okay, well, if a power series and a Taylor series is the same, then why do we actually, why don't we just call it one thing instead of having both of these names, okay? And so I am going to sort of demystify that a bit. It's more of a matter of semantics, but once you kind of see what I'm saying, you'll get the idea, okay? So here in general, if we were to take a function and express it, well, not a function, but let's say a power series, and express it this way, okay? And the key here is to say, well, how do we express C sub n, or the coefficients? Well, if I don't tell you specifically how I express those coefficients, then what you're seeing here is a power series, okay? So a power series is just, hey, we have a polynomial that has infinite number of terms in it, and I could write it in this form. So that's essentially what a power series is. When I say that, hey, I have a power series where my coefficients are calculated this way, that is what a Taylor series is, okay? And that's really the only major difference. So when we say power series, we're acting as if we don't know how we're going to express those coefficients C sub n. When we say we have a Taylor series, we're being very specific, and we're saying, yes, I know that I'm dealing with this certain type of power series when my coefficients C sub n are going to be expressed this way, okay? Now, it's important for us to understand that, because when we also look at binomial series, and I told you I'm going to do a separate video series for that. Whenever we look at that, you're going to see that, again, we're going to have a power series to start out. Basically, I'm going to represent a function as some polynomial, but the way in which it's going to look is going to be different. And so because of that, that's why, again, we have power series is the big umbrella. Taylor series is saying, hey, power series where C sub n is going to be this certain way. And of course, whenever we talk about binomial series, the coefficients are going to look different, and how we calculate them are going to look different, okay? That's the major thing. Now, with a Maclaurin series, not much to it. If we just let A equal 0, so the A's that you see here, or the A that the Taylor series is centered about, if you let it be 0, then it becomes a Maclaurin series, okay? So if you know a Taylor series, then you also know a Maclaurin series. So a Maclaurin series is simply just a very specific type of Taylor series where we center everything about A equals 0. That's pretty much it. Okay, so let's go ahead and review our responses for the first few questions that we had. I'm also going to briefly talk about question number 3. And I'm only going to do that briefly here because I'm actually going to address that particular question in another video and kind of tie it to the examples right away instead of just introducing it and then not talking about it for a while and then coming back to it. So question 1, what does power series expressions of a function look like? Well, we know it just looks like regular power series where in this case, our power series coefficients are going to be the nth derivative of our function evaluated at a divided by n factorial. And of course, we know that whenever we use this type of calculation here for the power series, then the power series that we're actually talking about is a Taylor series. Okay, and we also know that another popular type of Taylor series is a Maclaurin series, which is essentially just a Taylor series that is centered about 0, or we let A equal 0 in this case. So it's just this same power series where we just let A equal 0. So question number 3 says, how do we know the power series representation of f of x actually equals f of x? So in other words, we want to take some function that we know and we want to represent it as a power series or as a infinite term polynomial, essentially. And we want to know, okay, well, if I do that, how do we know if that particular polynomial is actually representing the function f of x that I wanted to talk about exactly to a t? Okay, so we have 2 theorems that address that. So the first theorem is going to be called the Taylor remainder theorem. And again, I'm just going to give you the summary of it, okay? And so the Taylor remainder theorem essentially says if we're picking x values that are known to make that power series converge, called the interval of convergence, and we know that the limit as n approaches infinity of r sub n of x, and what this function represents is the remaining terms of a Taylor polynomial, and I'll write it like this. So if we were to take our function f of x and write it out this way, where that t sub n of x is going to be the first n terms of our infinitely long term polynomial, and this is the remaining of those terms. So this is going to be terms 1 through n, and this is going to be the n plus 1 all the way to infinity. So if we're listing out the infinite number of terms for the Taylor series, or in this case, power series in general, we'll just take the first n terms here, and they'll look like this. The n plus 1 on to infinity, they'll look like that. And if I take the limit of the n plus 1 terms plus the n plus 2 terms all the way on to infinity, and it goes to 0, then I know this condition, and picking values of x within the interval of convergence for the power series will guarantee me that the power series representation of the function is mimicking the actual function exactly. Okay, so the polynomial that we come up with will be an exact representation of the actual function that we're dealing with. So that's what the Taylor remainder theorem says. The Taylor's inequality theorem gives us a way to be able to know, all right, well, what would our remainder look like, okay? And what's going to be an upper bound for our remainder? Or if we put it another way, what is going to be an upper bound for the amount of error that we could expect to get. Okay. And with that, again, not to try to make this too deep. So here, if we are listing the first n terms of a Taylor series, then of course the n plus 1th term should look something like this. Okay. And it's going to look something like that because this in general is going to take on the profile of a general term in a power series. Okay. And of course, if we're looking at the n plus 1th term, we're going to have an n plus 1 there. And whatever this coefficient is going to be the n plus 1th coefficient. So it's going to look like this. And then, of course, we got the x minus a. And you can kind of see how the c sub n plus 1 is going to look something like this here. Of course, the n plus 1 here looks like that. And we have the x minus a, which is the x minus a there. Okay. And again, all this theorem is basically saying is that, hey, if you want to figure out how much error you got, then you need to look at the n plus 1th term, because the n plus 1th term is going to be the biggest amount of error that you would have, okay, for these interval of x values that are going to be in your interval of convergence. Simply put, that is pretty much what it is. Of course, on the next page, I go through all the details of saying, well, hey, you know, this is going to be the upper bound, that we can get fancy and start using the squeeze theorem to show that your limit or the behavior of your upper bound as you begin to plug in higher and higher values of n in it, and of course your limit of 0, they're all going to be the same thing here. So since I know the limit of this is 0, here I got various ways I could show based upon what type of term this ends up looking like, that limit is going to go to 0. And of course, both of these would have to kind of smush this one in between. The error can't be any bigger than this. It can't be any smaller than that. And of course, this is what the behavior of the actual error is. If both of these go to 0, then I know we're good. Okay. And again, your function is exactly matching up with what your power series is matching up exactly with what your function is supposed to be representing. And so at the end of the day, that's all that particular theorem is trying to say. Okay. And again, when I say there's various ways that I could show the behavior of this n plus 1th term, as n approaches infinity goes to 0, I could use the ratio test, root test, some other convergence tests like what is that? Alternating series test. If what we have inside of here actually looks something like it came from an alternating series, we can use those things. Okay. The last thing that I say here is that we're also tying in the fact that what we're looking at here is going to basically look like a series, and we have this basic fact whenever you study series that basically says that if a series is convergent, then we know that the limit of the sequence is going to be equal to 0. And that's essentially what I'm saying here. If we know our power series converges, then this term here, which actually represents a sequence, it should go to 0. Okay. And no matter, how fancy of the test we use, at the end of the day, that is what should happen. And so that's why I mentioned that here. So now what we're going to do is do some examples. In this video, we're going to concentrate on Taylor series and Mclaren series. We'll wait to do binomial series in its own separate video here. All right, so let's get into this first example. So for this first example, we assume that the following functions f of x will have a power series, expansion, or representation. And we want to find out the Taylor series for that particular function centered at the given value of a. So we're going to have a couple of examples in example 1 here. So for this first function, we know that the function that we want to represent as a power series is going to be x minus x cubed, and we want to center it about a equals -2. Now, the first thing I want to say before we do this is that I picked this example because number one, it was simple. Number two, I wanted to show how we center stuff about a value of x that you wouldn't normally think to do that on, okay? Which is a is equal to -2. The other thing I want to mention is that f of x in itself is a polynomial. So technically, I wouldn't have to do this, but I'm doing this example just so that you can see, hey, we could have a polynomial be represented by another polynomial, you know, depending upon where we want to center it about, okay? So this is solely for illustrative purposes to show you how we can take some function and transform it into a Taylor series, okay? All right, so we have our function and we are assuming that we can express this function here as a Taylor series. And of course, we put everything in. This is us expanding out what the Taylor series would look like. And so in doing that, to figure out what our coefficients are going to be, we have to figure out what f of -2 is, f prime of -2, f double prime, so on and so forth. So if you see here, using this particular function, I go ahead and I plug in -2 in for x to figure out what f of -2 is, and I'll get 6. I take the derivative of this particular function here, and then I evaluate it at 2, and we see that's the derivative, 1 minus 3x squared, evaluated at -2, I get 11, and then I repeat that for the second and third derivative, okay? And I see that I end up getting 12 for the second derivative, evaluated at -2, and -6 for the third derivative. Of course, the fourth derivative, since the third derivative was just -6, then of course the fourth derivative is just going to be 0. And that makes a lot of sense because here we know that the function that we're dealing with is a polynomial in and of itself. So since it is a polynomial that has a limited number of terms, then that means that the power series representation of it, which is just another polynomial, should have a limited number of terms as well. And of course, whenever a polynomial has a limited number of terms, we know that there is going to be some point where if we taking successive derivatives, that the nth derivative of that polynomial is going to end up being 0, okay? That is what we're seeing here. So at this point, if we take all those values, like what is f of -2, what is f prime of -2 divided by 1 factorial, of course this is like 0 factorial, what is f double prime of -2 divided by 2 factorial, so on and so forth. If we go plug that in, then we see that our function can be represented this way. Or to make sure that this is clear, our polynomial, which we know is just x minus x cubed, can also be represented in the way that you're seeing here, okay? And notice that the difference is that everything is centered about a equals -2, or put another way, all of our terms have x plus 2 raised to some power in it, okay? And so when we say it's going to be centered about a equals -2, that's essentially what we mean. We want to write it to where all the terms is going to be x plus or minus some number raised to a power. And that's what you see here, okay? So at this point, what we have is the Taylor series representation of this particular function centered about a equals -2, okay? So this and this are supposed to be the same thing. The next thing that we want to do is we want to find out if this function and this power series is supposed to represent the same function. Then we want to figure out for what values of x is that actually going to be valid for. And of course, that is what finding the radius of convergence is and how that comes into play. So we note that, of course, this power series terminates. That is to say, has terms equaling 0 for values of n that are 4 and higher. And that's what I mentioned up here, okay? Now, this means that our infinite power series is really just a polynomial. And of course, I've addressed that before. Since the domain of the polynomial is a set of all real numbers, then it follows that our radius of convergence is infinite. And of course, what that means is that, like I've been saying before, this polynomial is going to represent this polynomial for all values of x, because the domain of this particular function is all real numbers. So that means that the domain of this function that terminates, which is a good thing, should also be all real numbers. So by definition, the radius of convergence has to be infinite, which means any x value I plug into here, and I get a y value out, I can plug in any real number x value into here. I'm going to get that same y value out. Okay. All right, so let's move on to example B, something that's a little bit more interesting. So let's take cosine hyperbolic, or cosh, of x, and we want to center it about a equals 0. Okay. So if you remember, we know that any Taylor series centered about 0 is essentially a Maclaurin series. Okay, so that's what we're actually doing here. The other thing that we have to remember is that cosine hyperbolic of x is just a shorthand notation for taking the e to the minus x and e to the x functions, adding them, and then dividing them by 2. Okay? And of course, sine hyperbolic, we're going to need to know that, is going to be the difference in between e to the x and e to the minus x, all that divided by 2. Okay. We lastly note that the derivative of cosine hyperbolic is sine hyperbolic, and vice versa. The derivative of sine hyperbolic is cosine hyperbolic. Okay, so we know that, and again, of course, I mentioned here that we just have a Mclaren series. So what this essentially does for our power series here is that when we have the x minus a raised to the n part of that, since a is going to be 0, we don't have to worry about that, and now it's just essentially x raised to the n. And so that is what you're seeing here. Of course, the coefficients are going to be the same. You know, your c sub n is just going to be the nth derivative, and it's going to be evaluated at 0 since our power series is being centered about 0, all that divided by n factorial. And of course, we're listing all that info out. So here, at this point, we need to figure out what f of 0 is, f prime of 0, f double prime, f triple prime, so on and so forth. So I go ahead and do that for a bunch of terms. And we see here that cosine hyperbolic of 0 ends up being 1. Sine hyperbolic of 0 ends up being 0. For the first derivative. For the second derivative, evaluated at 0, ends up being 1. For the third derivative, at 0. And we see that there's a pattern. Okay, so for every even numbered derivative, we're getting 1. For every odd number derivative, we're getting 0. Okay, so here we could express that in this way. Any even numbered derivative evaluated at 0 ends up being 1. Any odd numbered derivative evaluated at 0 is 0. Okay, and here when we go and express that again, so I've just kind of listed everything out here, so we see all these terms that'll end up being 0. It's going to look like this. And then of course here, since we're only really dealing with the terms that have even powers, then here you notice this n is going to turn to a 2n, and this n factorial here is going to turn to a 2n factorial. And so by rewriting it that way, that allows us, according to what we see here, that allows us to be able to have a good power series representation of what the actual function cosine hyperbolic is. Okay, and so now we have a power series representation for it. What we need to do now is to check out to see what values of x can we plug into this power series representation to ensure that for those values of x is going to match up to what cosine hyperbolic of x is going to equal exactly, okay? And for this type of power series, the result that we ended up getting, it's very easy for us to go ahead and use the ratio test in this case. And just so that you know, in most instances, unless you know you have something like an alternating series or something that looks geometric or harmonic series, you want to go ahead and try to use the ratio or root test, because if it does pass those tests, then you'll know that you have absolute convergence, okay, for whatever x values you find. So to apply the ratio test, just to kind of remind you here, we're doing the limit as n approaches infinity of a sub n plus 1 over a sub n. And of course, we're looking for a certain outcome, okay? And that outcome, we would like it to be less than 1. If so, then we know that our power series that we have is going to converge for whatever that particular inequality ends up being here, okay? So to make that a little bit more clear, I'll just erase this and say we want this. Do it like this, yeah. We want this to be less than 1. We can put the equal to there, but essentially whatever this comes out to be is going to be some expression of x, and it's going to have to be less than 1 in order for that to happen, okay? So if we go ahead and figure out what our a sub n is, which is essentially what our sequence is for this series, and then a sub n plus 1, wherever we see n, we replace it with n plus 1, and then we just do the ratio of the two and then take the limit as n approaches 0. So you see here that we do our ratio, and of course we're doing a lot of simplification here. We end up with this result. We take the limit as n approaches infinity of that result, and of course we see here that what we're looking at, we're going to have 1 over this 2n plus 2 times 2n plus 1. That is what we're actually going to take the limit of. This x here, because the n and the x don't match, it's going to be looked at as a constant, so we can throw that out, or pull it out, I should say. And then afterwards, we take the limit of what's left. Of course, this is a rational function where the denominator has higher degree than the numerator, so we know that goes to 0. So then we just have x squared times 0, which is 0. And of course, 0 is less than 1. And that's why I was saying here, I know I had the equal to there, but it really shouldn't have been there. Since this ends up being less than 1, then of course, this 0 being here tells us that it doesn't matter what value of x we have, the limit of that ratio is always going to go to 0. So that means essentially my radius of convergence is going to be infinite, which means my interval of convergence is going to be infinite. And thus, that means that this particular function, cosine hyperbolic of x, can be represented as this power series that we have right here. It can represent it for any value of x that we want. So for any value of x I want to plug in to cosine hyperbolic, I can plug it into here as well, and it will spit out the same exact y value, okay? So this polynomial that results is an equivalent function for cosine hyperbolic of x. All right, so I have 2 other examples that I want to do here, just to have you see some different examples of how all this works. This next example, we want to find a Taylor series for the function, in this case, sine of x, centered at the given value of a, which in this case is going to be pi over 2. And remember, all that's basically saying is that whenever we write out our power series, we're going to have terms that is basically going to have x minus pi over 2 raised to some power in it, Okay. Each and every one, of course, except for the first one when n is 0, because anything raised to 0 is 1. But every term after that, if we list it out as a polynomial, is going to have terms that looks like this in it. So that's essentially all it's saying. We're going to do that and then also show why for the power series representation of sine that the interval of convergence for it will be all real numbers. So we're actually going to show that as well. So very similar to the last problem that we just did. We're just breaking it up into two pieces. So let's find the Taylor series for this function sine of x. Well, of course, we're going to assume that f of x or sine of x can be written as a power series in the first place. And we're going to specifically do it as a Taylor series. Okay. So here we know it's going to meet this form of a power series where our c sub n's is just going to be the nth derivative evaluated at a divided by n factorial. And of course, a is going to be pi over 2. So this is what that would actually look like. And again, we need to find out what these coefficients are going to be, because that's the main thing that we need to know. So here you see that I work and do, let's say, the first, the function itself, and then the first 6 derivatives, just to kind of get an idea of what's going on. Of course, we know that the derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is going to be minus cosine. And then the derivative of minus cosine is going to be sine, and it just starts all over. Okay. If we evaluate sine of pi over 2, it's going to be 1. Cosine of pi over 2 is going to be 0. Okay. And then, of course, we'll get the negative in here because sine is negative there. And of course, I'll get the negative here because sine is negative there. So we see all that. So that means that here, what we're looking at, this is going to be our c sub 1 term. Okay. And I'm looking at it because we know what's here is c sub n. So my c sub 1 term is there. Up here, this is like the c sub 0 term. This is the c sub 2 term, and so on and so forth. Okay. So I'm not going to bore you with all that listing, but at the end of the day, once we have everything in place, we could expand out our power series term by term, at least for the first 7 terms like I've done here. And you see I went ahead and I've put in what the actual coefficient values would be for, of course, this is the c sub 0 one, c sub 1, c sub 2, c sub 3, c sub 4, c sub 5, c sub 6. And then, of course, we have some terms that turn out to be 0. And what we end up with is what you see here. And notice again how all of our powers are even. So when we kind of see what the pattern is, we notice that this pattern kind of follows each term is going to look like that. Okay, so the negative 1 raised to the n divided by 2n factorial times x minus pi over 2 raised to the 2n. Okay, so here we could represent our Taylor series as a series that looks like this. Okay, and of course, it's an alternating type series there. And that makes sense because we know sine has positive values and negative values depending upon what your angle is. So here we see that sine of x can be represented as this particular power series. And to be specific about it, this power series is a Taylor series that is centered about pi over 2. So now that we know what the power series representation of sine x could look like, we now want to show that that particular power series will converge for any value of x. And again, what that means is that that power series representation of sine x, if I was to plug in any real number x value into it and get a corresponding y value for that power series, it would be the exact value that I would get if I just plugged in that x value into the sine function itself, okay? So in order to find the radius of convergence here, we're going to do the ratio test again, okay? Path of least resistance to try to get to the end result here. So we figure out what our a sub n actually is, and remember, all that is what the corresponding sequence inside of your series looks like. And then a sub n plus 1, everywhere where you see n, you just replace it with n plus 1. And then from there, we have to take the ratio of a sub n plus 1 over a sub n and evaluate the limit, and of course do absolute value of it. So here, if I'm going to do the ratio of a sub n plus 1 over a sub n, it is just like having a sub n plus 1 times 1 over a sub n. And so that's what you see here, or the reciprocal of a sub n. So group everything together in this step. Things that need to be reduced to 1, I go ahead and do that. What I end up with as a result is what we see here. And all I've done is just rewrite this to make it look a little easier to deal with. From there, I take the limit of that result. And here, notice that all of this to the limit operator looks like a constant because it's not in terms of n. So I factored that out. All I have left is the expression that's in terms of n. And of course, we know once again that this just goes to 0 because we have a rational function where the degree of the numerator is smaller than the degree of the denominator. Okay, so that all goes to 0, and thus we just have 0 times this business, which is 0. And whenever we see that result, we know that any x value can be plugged into our power series, and it's going to match it up exactly. So it converges absolutely for all values of x. Okay. And so this is just my formal way of saying it. Since the limit goes to 0, Taylor series of sine x, which is this, converges for all values of x, because my radius of convergence ends up being infinite in that instance. All right, so with that said, that concludes the first video in this video series on Taylor and Maclaurin polynomials. In the second video, what I'm going to do is go back and look over those two theorems that I was telling you about, as far as like the Taylor inequality theorem and the Taylor remainder theorem. We're going to look over those again, go into a little bit more depth with them to explain what they are, and then we're going to see how that's actually used in an example for us to be able to estimate error. So that's going to be one of the things that we cover in that particular, or the thing that we're going to cover in that particular video. So I hope to see you there.